Hello, and welcome to the world of global wind patterns, which we have talked about a little bit in class, and so we're just going to go over some of the same ideas, and then add a few extra things that we haven't had time for in class. So, skipping the wind video, we did draw out the different convection cells and pressure belts and winds on the Earth, and just to refresh your memories, convection is the principle of warm, less dense things rising and cool, more dense things sinking. That's what convection is. And so we know, if we're talking about the air, we know at the equator the air is warm because the equator receives direct sunlight. So the air is getting really warm, therefore it's less dense, therefore it rises, and it starts flowing towards either the North Pole or the South Pole. And then it cools and sinks and makes a circle or a cell. So this pattern of warm, less dense things rising and cool, more dense things sinking is known as a convection cell, otherwise known as a convection current or a circulation current or a circulation cell, whatever you want to call it. So we do have multiple convection cells on Earth, 3 in the northern hemisphere and 3 in the southern hemisphere. And the main idea of these convection cells is that they are redistributing heat from the equatorial regions towards the polar regions. The equatorial regions receive more sunlight than the polar regions because the spherical shape of the Earth is not a perfect sphere. And so at the equator, the equatorial region is receiving a lot of direct sunlight. Therefore, it's being intensely heated. Whereas at the poles, because of the curvature of the Earth at the poles, the sunlight is hitting at more of an oblique angle, and it's not warming as much at the poles. So the heat that's being received at the equator then flows towards the poles. And that's what a convection cell is. So just to kind of recap, because you should already have a diagram of this that you made on your own. Again, we've got 3 convection cells in the northern hemisphere and 3 convection cells in the southern hemisphere. In the northern hemisphere, the convection cell and in the southern hemisphere, the convection cell between 0 and 30 degrees is known as the Hadley cell. So in the Hadley cell, you've got warm air rising off the surface, and as it rises, that air is also wet or moist or humid, whatever word. And that moisture, as it rises, it cools and condenses and comes down as rain around the equatorial regions. And then that air gets a little bit drier and a little bit cooler because it's up high in the atmosphere. And because it's cooler and drier, it sinks at 30 degrees north and 30 degrees south. And you will find a lot of your dry desert regions on Earth are located around 30 degrees north and 30 degrees south because you've got that dry air sinking. So that's the Hadley cell. Between 30 degrees and 60 degrees is your Ferrel cell. Same idea, the warmer air is rising, the cooler air is sinking, and then between 60 and 90 degrees is your polar cell. Also in this diagram, you can see some of the winds that are drawn on with the white arrows. You will want to know the names of the winds between the equator and 30 degrees. You've got the northeast trade winds in the northern hemisphere and the southeast trade winds in the southern hemisphere. And just so you know, winds are named based on the direction they originate from. So that means that the northeast trade winds originate in the northeast and they blow towards the southwest. The southeast trade winds, again, they originate in the southeast and they blow towards the opposite, which would be the northwest. So those trade winds are going to become important as we are talking about El Nino in the future. And the trade winds are significant for us in Florida because you do get a lot of dust blowing off the continent of Africa, blowing towards the west. And the reason why it blows towards the west is because of those westerly trade winds that you can see there. So the dust impacts us in Florida because it helps to lessen the chances of a hurricane forming. All right, so we've got our winds, and this video link is up on Canvas for you to take a look at. I really encourage you to do so. It's a really good video that outlines everything we're talking about here. And this is just another diagram showing you more of the same. So if you think of the 3 convection cells that we have in each hemisphere, their pattern relates to the different biomes that we have on Earth. Again, the arid or desert regions are concentrated around 30 degrees because of the convection cell that is at 30 degrees, which has a lot of dry air at it. So things that are going on in the atmosphere are impacting the distribution of different biomes on Earth. So kind of walking away from the convection cells and bringing us back to the winds that are blowing. Winds do not blow in a straight line. Winds will blow from an area of high atmospheric pressure to an area of low atmospheric pressure, but not in a perfectly straight line. And that's due to this thing called the Coriolis effect. The Coriolis effect happens because of the spin or the rotation of the Earth, and the fact that the middle portion of the Earth ends up spinning much faster than the poles, and it causes things to look like they're being deflected, either to the right in the northern hemisphere, also known as clockwise, and to the left or counterclockwise in the southern hemisphere. And the Coriolis effect only applies to large masses, like a big mass of air or ocean water. It does not apply to the way your toilet flushes or the way your bathtub drains. I put a few videos on Canvas for you to take a look at that explain more of the Coriolis effect, but the big thing I want you to know is that winds are deflected clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. So, wind and the atmosphere is not the only thing that impacts climate. The ocean can have an impact on climate as well. And wind affects currents in the ocean. There's 2 main types of currents in the ocean: surface currents and deep water currents. So what we're going to talk about here are surface currents. Surface currents occur at the surface, and because they're at the top of the ocean, they're going to be affected or impacted by the Coriolis effect. These surface currents are caused by the prevailing winds. So that means if the winds are blowing clockwise in the northern hemisphere, the ocean surface currents are going to move clockwise in the northern hemisphere as well. So they just kind of go together. And currents, depending on where they originate, can carry heat. If they originate at the equator, the current is going to be warm and carry heat. If the current originates near the pole, like the North Pole, it's going to be a cold water current. So these currents are really important in affecting climate, and currents flow into each other and form these big circulations known as gyres. That's what you're seeing in the map here. You may have heard of a gyre before when people are talking about the Great Pacific Garbage Patch, you know, big mass of floating plastic out in the North Pacific Ocean. And it forms because all the currents are flowing into each other and making a circle, like a little whirlpool, and pushing everything towards the middle. So these 5 gyres, again, are flowing clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. These gyres are formed by individual ocean surface currents. And you can see some of the ocean surface currents that are named on here, like we'll choose this one. This is called the North Atlantic Gyre. This one's the South Atlantic Gyre. But the North Atlantic Gyre, on this map at least, has 3 currents involved in it. The North Atlantic Equatorial, the Gulf Stream, and the Canary Current. So notice they're all flowing into each other, making a circular pattern. So you've got the North and South Atlantic gyres, the North and South Pacific gyres, and then there's just one in the Indian Ocean. Here's a better map of ocean surface currents and the gyres, because again, the currents flow into each other to form a big circulation gyre. So again, we'll focus on the Atlantic. So you've got the North Equatorial Current that flows into the Gulf Stream. The Gulf Stream carries warm water. That warm water also is carried across the Atlantic Ocean and ultimately flowing by Great Britain, keeping the climate here relatively warm, as opposed to the east coast of Canada. Like if I were to draw a straight line across, I don't know what city of Canada that is, but this region over here is significantly colder than this part of Britain. And that's because there's a cold water current flowing by that portion of Canada. So currents are really important in helping to regulate the climate of every place on Earth. I want you to look at the 5 gyres on here. And aside from the clockwise versus counterclockwise, see if you notice another pattern. The pattern is that in a gyre, you have the cold water always happening on the east side of the ocean, and the warm water is always on the west side of the ocean, no matter what gyre we're talking about. Or you could say, if we're not talking the ocean and you're talking about the continent, you can say the west side of the continent always has cold water next to it, and the east side of the continent always has warm water next to it. And again, that's a result of the way the winds are blowing due to the Coriolis effect. So these ocean surface currents, in conjunction with air movement in the atmosphere, are what has a huge impact on climate. And that's what determines what biomes we have on Earth. Just like it says here, ocean currents plus solar energy equal our different climate zones, or equals our different biomes that we have. And again, just pulling up this map showing you the different biomes. So to wrap it up, wind plays a huge role in regulating the climate on Earth, and wind also affects the ocean, which means that oceans also play a huge role in moderating the climate of Earth. So that's all for now. I'll see you in the next video. Bye-bye.